Hello, my name is Isabella and I will be your host today for another mathematics video brought to you by RJ. Today I ask you, what is the residue of shifting partial sums? First, let me show you an analogy of what is a residue. I have here a cookie. Suppose I take a bite. I ate a piece of the cookie, and here is the other part of the cookie. These crumbs are the residue of the cookie from what I ate. The residue is the little pieces of what is left over when you take away a portion of something. We can use this same concept in mathematics. I'll let you have the rest of the cookie. Now, what do I mean by shifting partial sums? Let's look at a simple example of a partial sum, namely the series of natural numbers from 1 to n. Of course, this is an infinite sum. To make it a partial sum, we choose a stopping point, say 4 or 6 or 10. As an example, let's just choose 6. We have a partial sum. This is the general formula for calculating the partial sum of natural numbers from 1 to n. Since n equals 6 in our example, we can easily see that the partial sum is 21. Here is where it gets interesting. Suppose we want to add the next number in the series, which is 7 in this case, to this partial sum, but we also want the partial sum to still be equal to 21. This means we have to also take away some numbers at the beginning. The question is, how many? We already have a general formula for this partial sum, which gives us a sequence called triangular numbers. So, all we need to do is determine which n gives us the partial sum of at least 7. I say at least because if we take away anything less, then obviously we did not take away 7, which is what we need to do. Even though we are using a specific example, I'm going to show the general solution to this and the steps. I'm also going to use m to represent the next number in the series. Here we have a quadratic equation. So, we need to use the quadratic formula to solve for n. I'll let you work out the steps, but I'll show you the result. Typically, we would also have a minus here. But if we did, then n would be negative, and n cannot be negative. So we can eliminate that possibility. There is another issue here. Even though this gives us our solution for n, based on this formula, n might not be an integer, and n must be an integer. For instance, in our example, m equals 7, then we get, this is clearly not an integer. As I said before, we need to take away at least 7, so we need to find the next highest integer of our solution for n, if n is not an integer already. To do so, we place our general solution for n inside the ceiling function. Now we substitute this into the general formula for our partial sum. We now have a least upper bound for how much to take away at least m. The final step is to subtract m. We now have a formula for the residue of shifting the partial sum of natural numbers from 1 to n. Remember, m is the next number in the series. Going back to our example where m equals 7, we have the residue of 7 in our partial sum is 3. Another way of seeing this is the way we originally had the partial sum from 1 to 6, which is 21. Then we added 7. We then needed to take away 7, but our least upper bound is 4. So we take away 1 through 4. 5 plus 6 plus 7 equals 18. We need to add 3 to obtain our original partial sum of 21. Thus, the residue is 3. I challenge you to find formulas for residues of the shifting of partial sums of other sequences. If you would like to see RJ's formula for the residue of shifting perfect squares in the consecutive odd series, the link is in the description, or you can search for it on the online encyclopedia of integer sequences under A3485596. I'll leave you with two final questions. What happens when we reiterate this process for the same sequence? And can you think of ways this process could be important or helpful? I hope you enjoyed the video. Thank you for watching.